Hello everyone, and welcome to the fourth event in our special online meetup series hosted by the Web3 Developers Underground. Before we dive in, let me briefly introduce you to our community. We are a group of Web3 developers founded on open source values by Shaoli Rejwan and Roy Osherov. Since our inception 3 years ago, we've consistently hosted in-person events, bringing together some of the brightest technical minds in the space. As many of you know, we've recently expanded to online meetups, and we're committed to delivering top-tier technical content to the global Web3 community. We're thrilled to have you with us today. Make sure to follow us on all platforms, X, Luma, Meetup, YouTube, Telegram, and more, to stay in the loop for future events and updates. A special thank you to our community sponsor, Master Key VC, an early-stage venture capital specializes in infrastructure and deep tech focused across all Web3 ecosystem, with a team of 16 world-class cryptographers and technical experts, led by our managing partner Shaoli Rejwan. Master Key operates across all major global crypto hubs. And now, without further ado, I'm honored to pass the mic to a dear friend of ours, to our community, one of the greatest minds in cryptography, the man who joined MPC space in the late 90s, thinking he was late in the game, but went to drive some of the most important breakthroughs. Dr. Yehuda Lindell, head of cryptography at Coinbase. Also joining us today is a longtime friend and a dear community member, and of course our moderator for today, Johnny Time, a core part of our community. Yehuda, Johnny, the stage is yours.
Thank you very much. Okay, so I will start sharing my screen. If other people want to show their faces, I'd appreciate it. I prefer to actually speak to people rather than to, that way I can see if anybody actually is following me or just washing the dishes or I don't know what. Okay, so I am going to present and talk about Coinbase's open source cb-mpc library, which we released quite recently, actually, a couple of months ago. I'm going to talk about the library and why we did it and what it has. And this is joint work, of course, with the entire Coinbase team. But I also have Arash here, who is going to take over from me. After I present the more, let's say, theoretical side of things, Arash will actually take you through more details of the actual code, and he'll run the workshop for you. Okay, so what is MPC? I think it's pretty well known by now in the field, but I'll spend one slide in any case. So secure multi-party computation, or MPC, is a cryptographic method or technology that enables multiple parties to jointly compute a function over their private inputs without revealing those inputs to anybody. So it enables you to compute together, but while maintaining privacy and other properties. And it turns out to be ideal for crypto key management. And the reason is that the function that we want to compute in this case is just signing. And what we can do is we can take the private signing key, and instead of putting it on a single machine where it's vulnerable, we can split it into multiple pieces and give it to different people or entities or machines. And then they need to all collaborate, or a quorum, if we define a quorum, they need to collaborate in order to sign. And if you only are able to corrupt a subset of those parties, or if there's a quorum that agrees to sign, then you actually cannot do anything, and the transactions that won't take place, and also the key will not be revealed. And this eliminates single points of failure or single points of compromise, so you can't break into any single machine and steal the key. And of course, that prevents theft, but also prevents something more, which we call key misuse. So I don't have to steal your key in order to steal all of your money. All I need to do is actually generate a transaction that transfers all of your money into my account. So just one key misuse and it's all over. And so even if I have like a perfect HSM, which no one can steal the key from, but if I get to the machine that issues the transaction to that HSM, then I can bypass all the controls and I still have a single point of failure. And with MPC, I can enforce policies or anti-fraud techniques on multiple different machines. and ensure that everybody has verified that and everybody is approved before going forward, and there's no longer any single point of compromise that I can get there and steal or misuse a key. So that's MPC, and of course it's relevant for custody, consumer wallets, and so on and so forth. So Coinbase has released cb-mpc, which is an open source library for threshold signing. And the first question is, why open source? Why should we open source something which has really many person years of investment and expertise is in building? So the first reason is we very much believe that better security is better for everyone. So MPC is well recognized to be the right or an excellent fit as a solution for key management applications in crypto. But MPC expertise is very hard to come by. There is a lot of demand for MPC, not a lot of expertise, and even with expertise, there are many different levels of expertise. In Coinbase made a huge investment in MPC. We have a lot of expertise. We spent many years developing and implementing MPC beyond researching it. And that's very different to what you find out there. And in fact, at least in our opinion, most open source libraries that you can find out there are not production standard. And we believe that any breach to any organization is bad for the industry and therefore bad for Coinbase. Coinbase would like to have a piece of a bigger pie, which will end up being much bigger than saying, oh, okay, if they're breached, then everyone will come to us. Actually, it doesn't work that way. When others are breached, what happens is customers, consumers lose faith in crypto, get scared, and therefore we want everybody to be more secure. So that's the first reason. The second is just transparency for our customers. We use this for custody. We use this for retail, for in general securing our assets. And we want our customers to be able to see what we're doing. I do want to stress that it's not the code in the open source is not the exact production code. And the reason is that the production code has very specific flows that are relevant and suitable for Coinbase's specific setup. But the open source library, we want to be a general purpose library. And as such, we had to make certain changes, but it's really just taking and removing the specific flows and making them more generalized. So yes, this is actually a very much a production library. It's production ready for use, and also customers can take a look and see very clearly what cryptography we're actually using. And finally, we believe that it can improve our security because now we have open source that can undergo external scrutiny. There's a bug bounty program. If we've made mistakes, we can get publicly shamed. Not so happy about getting publicly shamed, but I would rather be shamed than have a bug in my protocol. So that's certainly a choice, a conscious choice that we've made. Better security is really what we want. So what are the key features of the library? We have support for ECDSA signing and for EDDSA or Schnorr. They're essentially the same thing. That includes key generation, signing, secure publicly verifiable backup. Publicly verifiable backup is a type of backup where you encrypt the private key shares, but you encrypt them together with a zero-knowledge proof that actually what's encrypted in there is the correct backup. So you're able to look at the ciphertext, you're able to look at the backup and verify that indeed encrypts the correct private key without having access to the backup secret key for decryption. So that means you can verify it's correct without opening up any vulnerabilities. And this prevents something from happening, for example, if one of the
Yehuda, I think you got muted and you're not sharing screen. Still muted. Is it just me? I cannot hear Yehuda.
No, it's not just you.
can you hear me now?
Yeah.
Okay, so I'm back. So I'm not sure where I was. I was in publicly verifiable backup. Bottom line, you can publicly verify the backup is valid and therefore prevent a very, very bad case where your backup was invalid and you lose all of your money. I always tell people that there's only one thing worse than having all your money being stolen, and that is having you lose all of your money. It supports two-party and multi-party, so you can have, again, two-party protocols, but also any number and quorums, as I'll show in a second. Of course, two parties can be a special case of multi-party, but sometimes there are specific protocols for two-party that are more efficient. It supports threshold cryptography and, in general, rich access structures. So yes, you can define that you need 5 out of 12 people to sign, but you can also say, I want 5 out of 8 people in this group together with 3 out of 5 in this group. And you can define these sort of rich access structures, which can be very helpful in advanced custody situations where maybe you have different people on different teams, or possibly even between different organizations that need to approve an operation. So we're really trying to think about this open source library as something which people will use in production. It's not a toy or something to look at. It's really something that we hope is very useful. The library comes with a very rich documentation, including theoretical background for everything we do, specifications, benchmarks. I'll talk about them more a bit later. We believe our approach is security and rigor before performance. The library is performant, but it's not, there are certainly some protocols which are more performant than what we've implemented, but our aim is to be very conservative in the security that we're taking. And it is a C++ library, but it does have Go wrappers. So for those who prefer to write in Go, you have, I studied computer science in the 90s. So for me, I prefer C++, but probably one of the, a dying breed, maybe even literally. But anyway, Arash will talk more about that in the second half. In terms of the structure of the library, we have 3 main categories. Crypto is not a very low level, but it's quite low level. So you'd have things like modular arithmetic, random number generation, elliptic curve operations, Payer, El-Gamal, commitment, secret sharing, threshold encryption, all of those sort of things. We have ZK, which is a whole series of zero knowledge proofs of all different kinds for our protocols, elliptic curve based, Payer, range proofs, and more. And they're compiled into non-interactive proofs using Fiat Shamir or Fishlin, if you're familiar with those. If not, that's also okay. The higher level, that's the ones where we're actually getting closer to the actual signing protocol, but some of it is on the way as well. So you have things like coin tossing, oblivious transfer, which is used in many protocols. I mentioned publicly verified encryption. Of course, you have distributed key generation, HD derivations. You can do, you can build HD wallets in MPC, and of course, EDSA and Schnorr and ECDSA. Now, what's important to note here is that you can use the library at the very high level, but you can also use it at lower levels. So you want to implement a different protocol, but you don't have to now implement everything from scratch. You can use all of the tools that we've built in and start from there, and you'll already be in a much, much better position. Again, secure, not just in terms of time to market to make it easier for you to implement, but also you have a much more secure base to start with. Coming back to the theoretical rigor, we have theoretical justification and proofs for all of our primitives at all levels. We either refer to a published paper, but we don't rely on any paper that's been published. Any paper that we refer to, we have independently reviewed within our team and within an additional team in Coinbase. Not every published paper, unfortunately, can be relied on to be correct. So we independently verify that. Where there isn't, we've written full proofs of our own. Some of the documents are very long with very detailed proofs. Others just refer to a paper. You'll be able to see that. We have exact specifications to bridge theory and implementation. Anyone trying to take an academic paper and implement will realize there's a very big gap. It just refers to some other primitive. It's unclear how I'm supposed to implement that. Maybe it says use oblivious transfer. I don't know which ones I should use. There are those that are known to be buggy, but you won't necessarily know that online. So all of that is covered in the specifications, which really tells you exactly what is implemented, and you can compare them and validate yourself that indeed it matches, the code matches the spec and matches the theory. So in the repository, you can see this. Here's a list of all the different categories. Each one has a specification document, a theory document, and a pointer to the relevant code. We also have additional documents, a design principles document, which is more like our cryptographic philosophy. It's a very conservative one, and we outline it there. We have a secure usage document, so if you are going into a low level, not just saying sign. If you're just signing, you don't really have to know anything about how it works, but if you want to use it at a lower level, there are some things you do need to know, and we outline them in that document. And we also have a document talking about our approach to constant time computation. Our aim is for everything to be constant time, or to be more accurate, for everything to the running time to be independent of the private data, so it doesn't leak side channel information about private keys. So here, for example, you can see what it looks like for the specification next to the actual code. On the left-hand side, you see specification for EDDSA two-party signing. And on the right-hand side, you see the code itself. So, for example, the specification will say that the first party P1 needs to choose a session identifier, a random 128 bits, then choose a random value K1 inside ZQ, so between 0 and Q minus 1, where Q is the order of the curve. Then you multiply K1 times G, which is the elliptic curve generated, to get R1. Then you you commit to that, and you send it. Now, on the right-hand side, you can see it just looks exactly the same. So if I'm P1, I will randomly generate an SID of length computational security parameter, which is 128. I will choose a random value K1. This enables you to do batch, but the principle is the same. I will then multiply K1 times G to get R1. You can see that we have overloaded the operations here. So the elliptic curve operations just look the way they look in the spec. Then I can generate a commitment, and I send it. And you can just follow each step in exactly the same way. Here, for example, here you also have a zero knowledge proof. That zero knowledge proof proves that you know the discrete log. And here I can just call that here. So it really very, very closely matches. It's very easy to be able to ascertain that the code follows the spec. And then later you can verify that the spec follows the theory. And then you have an end-to-end validation that the protocol is doing what it's supposed to do. I won't go through all of this. I think it's not necessary for this presentation, but it's just worthwhile seeing that you're able to do that mapping one-to-one. In terms of performance, I said that we chose better security over better performance. In our experience in blockchain applications, a few extra milliseconds rarely matters. I won't say never matters, because there are many different applications out there, but it rarely matters. Having said that, the library is still very performant. So, for example, for two-party ECDSA, the Lindell 17 protocol, which is widely used. In the paper, the original paper talks about key generation of 2.5 seconds. It takes 291 milliseconds in our library. That is not just better programming. It's primarily additional research which we've done then in order to improve the zero knowledge proofs and their performance, and therefore we get this much better performance. 291 milliseconds for key generation is really good, and for signing 18 milliseconds, again half the time what's in the original paper. Same thing, a little bit better programming maybe, but there are additional algorithmic and cryptographic improvements. Actually, the programming is actually a lot better, because it's Coinbase production software rather than academic software. But the fact it's production ready usually often means that you take penalty hits, because you have to do a lot of verification, sanity verification for absolutely everything. So we're actually getting much better performance even with all of that. So the combination of higher quality code, better programming, and better algorithmic solutions. And we also have another method which we call enhanced security signing. Or it's called the original paper has this feature that if certain errors detected, then you need to abort all executions. And in applications where you might be running many things at the same time together, that can be a problem. So you can add here a different method which isn't affected by that, and that will take 72 milliseconds. Again, for blockchain applications for ECDSA, this is very certainly good enough. There are full benchmarks on the repository just to show you what it can look like. So for the lower level here, you have elliptic curve operations. You can see how much it costs to add two elliptic curve points or multiply an elliptic curve point by a scalar. So these are all in microseconds. And you can also look at the suffering at the high level signing protocol. So here you can see this is EDSA signing. You can see the total time is around 48 milliseconds. But you can also see in each round how much time each party spends, and also the size of the message that they send and receive. So you really have all the information you need to understand how this will work for your application, or how you need to optimize your setup to be able to run this for whatever use case you need it for. In terms of community and contribution, so that's the GitHub. It's the MIT license, so unlimited use. You don't have to do anything. You can use it in whatever way that you want to. As I mentioned before, we really want people to use the library. This is not a have a look and see how nice and shiny this is. We really intend for people to use it. There's also a public bug bounty and security reporting method. It's on the repository page. Please try and break us. On the one hand, I hope you don't succeed in it, but I hope you don't succeed because there aren't any major bugs. But if there are, please find them and get a nice bounty and make the world more secure. So in summary, cb-mpc is a production-ready, robust open-source MPC library for threshold signing. It's intended for use for key protection or management for consumer wallets, institutional custody, exchanges, and so on. It has very strong theoretical foundations, including extensive reviews internally and externally and audits. It's the first release now. We have a very rich roadmap that things will be coming, but already as it is now, it gives you everything you need to build a very, very strong custody or wallet solution for whatever use case you need. Thank you very much. If there are any questions, we can take them now before we move over to Arash.
First of all, thank you so much, Yuda. Can you hear me?
Yes, I can.
This is really interesting. So I will just quickly introduce myself. I'm Johnny, the moderator today, Web3 security educator. I check out my YouTube channel, Johnny Time, and MPC was always like super interesting for me. And I saw you wrote like consumer wallets. Are really users using MPC wallets, or it's more like DeFi protocols, exchanges, and so on? Like how easy it is for my personal funds, for my self-custody wallet, how easy it is to use this? Does this open source library, can it really be beneficial for the end user?
So I don't think that an end user will take the open source library and write a bridge between that and their MetaMask wallet. That's not what I'm saying. What I'm saying is that if you are building a consumer wallet and you want to build MPC in, and there are certainly multiple consumer wallets. Zengo is one example, but there are others, and there's many startups I know about that are looking using MPC to build consumer wallets. Then what I'm saying is, don't go and build the MPC yourself from scratch. You don't need to do that anymore. You can take what we have in this library.
Cool. So it really helps, like if it's DeFi protocols or wallet projects, to not reinvent the wheel, and they can use like a battle-tested Coinbase library or code with like saves hours of work, avoids security issues, and so on.
Exactly, and I would say it saves months, many months of work, not hours. And it protects you from making major errors because it's actually very difficult to do well. So yes, absolutely.
Cool. So we have some questions from the audience. One question: why have you chose to create lib based on High 18? What's the difference between this and cg-mpc, DKLS? Forgive me, guys. I'm a newbie in cryptography. So all
okay.
Like...
So the protocol that we have for ECDSA, why we chose that one? We chose that one because that's what we're currently using. DKLS, actually, we are looking very closely at adopting that now also in Coinbase, and therefore that will come in a future release. In the library, that's our intention. DKS I like a lot actually because of its simplicity, and simplicity is excellent for security. So the reason we started with the protocol that we have is because it's something that we have very strong familiarity with, and it's also a very conservative protocol design. So that was our choice, but DKS is indeed on our roadmap.
Cool. Amazing. So we're going to have some practical workshop now, right, with Arash. We have some prerequisite. We sent a doc here in the chat and also in the online event page. So there are some tools that needs to be installed. If you guys haven't installed them, please check out the link and try to install the prerequisites.
I think there are a couple of people with hands up, if that's...
Oh, yeah. Yeah, I see one more question just pop up now. What hardware was used for the benchmark? I mean, I see that. Do you see any other questions? I see them in the chat.
Oh, in the chat I didn't see. Okay.
Yeah.
All right. What hardware is used for the benchmark? Arash, do you want to answer that question? I think it's written in the repository, no?
Yeah, this is the standard GitHub CI runner machines. So I can give you the exact thing by looking it up, but nothing special is what I'm trying to say.
Cool. Yeah, I see that there is also now updated link, which is better because before I didn't see links to install C++ on Mac, and now I'm going to install it. So guys, feel free to install all the prerequisites, and we will start in a second with Arash. Arash, you want to begin or give people some time or help them with the installation?
Yeah, I can help them with installation. Sorry? Yeah, I can help them with installation. However, I don't see a share screen. Oh, yeah, now I see. Great. All right.
So I see that there are still questions popping up for Yuda. So maybe in the meantime, when people install the prerequisites, they can also shoot the questions here, and Arash and me will try to help. But meanwhile, Yuda can answer some questions, right?
Should I answer by text or by voice?
I guess by voice would be better so everyone can hear.
So the question was, when you showed the table with the structure and supported protocols, are they all used in the high-level implementation? I would say yes. Certainly the very vast majority. There might be here or there a low-level primitive that isn't used, but yes, they are all used somewhere in a high-level protocol, or almost all.
I think there was one more question before. I'm not sure the context, but I will try to find it. It was, how many rounds does it support offline pre-signed like CMP?
So we don't support offline pre-signed for the reason that you can't actually prove that secure with the definitions. For ECDSA, it's extremely problematic. For Schnorr, EDDSA, it's possible, but not according to the definitions that we follow. So we don't support pre-processing them with just a single message at the end. I'm sure there are some people who want that, but I would argue that most applications probably don't need it. But in any case, it's not supported. If you want to build that, that's where you could start using the lower level and make that choice yourself. But in terms of our conservative approach, we have decided explicitly not to do that.
Cool. So I'm already installing. Guys, feel free to shoot more questions at Yuda. His time is valuable, and meanwhile he is here, he can give you all the answers you need. So in general, if you're curious about MPC, about the library, feel free to ask.
I see. I found some additional questions. So clarification on terminologies.
Oh, that was me. I just made it.
Okay.
Yeah, on the question, I mean, I answered in chat, but I can talk about it now as well. So instead of using React mobile app or WASM, I just want to clarify what the goal is. The goal is to help someone build an MPC-based wallet and then provide the API or whatever other thing that they need to their users. So the example and the workshop that we are going to demo is going to be a web-based thing, which is going to show how your front end can communicate with a MPC-based backend. So it is web-based, but I just want to make sure that this is the goal. The goal is to help people create a MPC-based wallet service, essentially.
Cool. I know that usually MPC, when it comes to MPC, we have multiple servers and there is some kind of infrastructure needs. So is there any explanation of how to set up the infra when it comes to running the code of the backend of the MPC service?
So we have, let me see if I can go and find the document. Okay, so in our repository, if you go to docs and then secure usage, this defines some important things that you need to pay attention to when you are setting things up, specifically on the networking side. What you need to implement, what the properties of the networking will require, and this is the properties between those different machines when they are talking with each other. How should that communication channel be protected? And also we have this note about if I can find it. We have this note about the players' IDs. Essentially is their certificate. Is our recommendation. So these are the only. Yeah, I can't find this right now, so I'll send you later. These are our only two main things. Other than that, how you set up your AWS or your other part of the infrastructure is your choice. As long as it follows best practices, you should be good to go.
Yeah. Thanks. No, I'm just wondering if like someone might think that they are secure by using MPC service, the library, but they install all the components on one server and like 3 different signers, same server, then you lose security. So it's not only about the code, it's also about the infra.
Right. Absolutely. So definitely different servers, ideally different cloud providers even, and even you can go one step further and go use different environments, a Linux and a Mac and a Windows. So the more variety you have, the harder it is to break into an MPC machine. So on the worst case is exactly what you mentioned. Put everything in one machine. You have the illusion of using MPC, but everything is in a single machine. And the other case is that everything is in different machines, different providers, different operating systems.
Yeah, so the more diversity, the better. Maybe in the meantime, we can give us a short intro about like what demo are we gonna launch today, like what we're gonna see, like. Yeah,
sounds good. All right. Yeah. Hopefully, people. Yeah. Anytime that people have questions about installing stuff, let me know, and I can pause and help. All right. So what I'm going to do is first show you what you will see right now in your machine after you install the stuff, and then walk you over what the goal is and how we want to change this. All right. So these are 4 different processes representing 4 different parties. And again, this is because this is a demo. Everything is running localhost. So don't do this in production, of course.
Don't do it in real life. Only at home, not in the production.
Yes. And all right. So the demo is that we first create an MPLS connection between them. So these connections are created using self-signed certificates, and the instructions walk you through how to create those self-signed certificates. Again, in a real-life scenario, use proper certificate and a PKI system. Then we have these 4 parties. All parties are going to participate in generating the private key, and public key for that wallet, right? And in this setting, party 0, we are going to call it the leader. Leader is going to choose configure the operation, and everybody is waiting for that choice. So let's say that we want to do a threshold signing. I will describe what threshold and access structure and all of that mean as we go through the workshop. But for now, what this means is that when we get to the signing, we want only 3 out of the 4 people to participate. All right, so that's what this number 3 means here. So we do the key generation, everybody participates, they generate the key, and they get a share of the full private key, right? So no one by themselves on their machine has the full private key. Everyone has a part of the private key. How everyone gets the full public key. And then we go to the signing phase. In the signing phase, again, everyone is waiting for the leader to make a choice. And since this was a threshold operation and only 3 people participate, the leader can choose what are the other 2 parties that are going to play with him and create a signature. The leader can choose the message as well. And then they can run the signing protocol. So as you can see, party 2 was not chosen, so it didn't participate. The other 2 parties and the leader together participated in a 3-party MPC protocol, and the leader obtained a signature. So we can verify that this signature is indeed valid by using any online tool or even OpenSSL. So this is just some tool that I found. You can paste that is the public key field. I need to paste it in the signature field. And this is the public key. And let's paste a message. If everything goes according to plan, as soon as I paste the message, I should see a valid here. Great. All right. So the signature is indeed valid, and it is verified by another third-party program. One thing, so our goal in this workshop is to start from here and then change it to do a couple of things. First, instead of generating an ECDSA protocol, we want to ECDSA signature, we want to generate an EDDSA, and then use that to submit a transaction to Solana. All right. So hopefully, if everything goes according to plan, by the end of this workshop, you can generate a signature, submit a transaction to Solana, and then see the funds transfer. And the other thing that we can do is play with this threshold or this access structure that I was alluding to. Instead of having, for example, 3 out of 4, you can have more variety or different ways of defining your parties or who participates. For example, let's say you want to say that if in a company, for any transaction, you'd absolutely want the CFO to give you the thumbs up, right? And then either CEO or COO should participate, right? So you will have one mandatory and then one of the other 2. This is different from saying that any 3 people can participate. So you can create these types of access structures, and that's our goal in this workshop, to teach you how to create these different access structures. Finally, another thing that we want to do is show you how you can back up those private shares, right? So you have those private shares, you did the DKG, you have those private shares, and now you want to make sure that they are safely stored somewhere. You can easily encrypt them and put them in a AWS or some other backup solution, but you may not be sure whether your backup was successful or not. So in this workshop, we will show you how to use a publicly verifiable backup solution, which gives you the assurance that your backup is good without decrypting it. So that's the high-level overall plan for this workshop. Any questions so far?
Yeah, I can ask 2 questions. One is, the configuration of the leader is only initially, and once the parameters are set, the leader cannot change anything about the thresholds or the required signers and so on? This is first question.
In this demo, right? In this demo, you cannot change the leader, but in a real world application, for any signing instance, you can choose who the leader is, and the leader doesn't need to choose the participant. Everybody needs to agree who the other participants are. For the purpose of this demo, to make it simple, we just choose the leader, and everybody waits for him. And the other thing you mentioned is changing things or changing access structure afterwards. We do have that capability in our internal code. We are working on creating an open source version of it and releasing it in future versions.
Cool. And another question. What's the main here? I understand that in MPC we split the keys to different parts, and then you need all the parts in order to sign a message. But
Right.
why would you use MPC rather than multi-sig wallet, where you have a smart contract that requires, let's say, 3 signatures out of 4, and instead of just splitting the key, just use 4 private keys? Like, what's the advantage or use cases specific for MPC?
So first of all, you just have one signature. It's just a lot simpler. It's under the hood. You don't have to manage the complicated smart contract wallet, right? The public key is always the same, and that address or that wallet address remains the same, and you can change the participants or different access structure however you want without ever interacting with the blockchain. Also, you can choose different ways of backing up your keys, and you are not necessarily tied to a specific way that a specific blockchain or smart contract is instructing you to do. So you will have a more general solution that will work for every application.
I'll add to that. I'll add to that that you gas in terms of gas fees, it's certainly much cheaper, especially if you have very complex access structures, a large number of parties. So that's also taken into account. And I forgot what the last one was. I had another point I wanted to add. 1 second.
It's already good enough. I'm sorry.
Also, if you're in an organizational setting, then like you're in think about someone providing custody or something for another organization, and you have the keys split amongst multiple different employees, maybe between you and also between the consumer, so or something to that effect, depending how you want to set it up. Then what happens if an employee leaves, another employee comes back? Replaces that person. Then now you have to start actually interacting on chain for everything like that. You may not necessarily want that to be public. You may not even want the access structure or what you're actually doing to be public, but certainly you don't want to start interacting on chain for every key every time an employee comes and goes or something like that. So that's also a reason why MPC, you can do it all under the hood and doesn't actually affect anything on chain.
Cool. So it makes everything more efficient, more like cheaper in terms of gas, and it essentially moves the authentication and the encryption to be off-chain rather than in like smart wallets or multi-sig wallets where everything is on-chain, more complicated, more expensive, and so on. But does it also add a layer of centralization in that sense? Like when it's like a multi-sig wallet with multiple signers, everything is transparent and on-chain, and MPC, like no one knows what happens in the MPC infrastructure.
So I don't think it's centralization. It's true that for accountability, if you want accountability in some sense, then multi-sig will give that, or you give you on-chain accountability. You can build accountability into MPC, at least in some sense. There's been
your knowledge, right? With ZK proofs.
Sorry?
With ZK proofs, I assume.
Yeah. You can, but it's not necessarily bidirectional. Like you can certainly prove that you participated, but it's not necessarily, at least with standard signatures, possible to prove that, at least what from to the best of my knowledge, to prove who did participate if they just, a group went aside and generated not using what you asked them to do. So it's not full accountability, but sometimes you could do a mix. Let's say you wanted to have, you had a backup key and you had a regular key. And if the backup key was used, you want that to be on-chain accountable. And otherwise, then you can use to do 2 out of 2 or 1 out of 2 multi-sig. One would be using the regular MPC, and the backup key would be separate, and you could see on chain if that was the case. So you can do a mix of things as well, really depending on what your application is.
Cool. And I think you have another question for Matan in the chat.
Okay, let me see.
Yes, everything is UC secure, so you can run all protocols concurrently with all other protocols. There is no need to terminate anything when cheating is detected. As I said, the only protocol where that can be an issue is Lindell 17, and you have 2 functions. One is called sign, and that's the standard one. There's no problem with global abort or anything. And if you choose to use sign with global abort, that's a different function which is more performant. You should only do that in, for example, if you're in a wallet from a mobile that you know is going to be sequential. But yes, everything else is fully concurrently UC secure.
Cool. Let's move on with the workshop. All right.
So now I want to essentially walk you over the code so that you understand where everything is, which will make it easier for you to actually do the workshop. All right. So if you want to see what is happening under the hood in the C++, and for example, see the actual cryptographic implementation, you need to go under SRC. That's where everything is located. For example, the protocol that was showing in the presentation is in eddsa. If my eyes help me, is eddsa.cpp. So. Right. Yes, of course you need to follow, and that was the 2PC. Here. So you can find that protocol here. So that is not the focus of this workshop, although that is the main contribution of the code. That's not the focus of this workshop, because we just want to show you how to use this underlying implementation. Now, the other thing is, if you want to see all the specification and how they match the C++, you would go under docs. If you don't care about the specification and theory document, I would still strongly recommend that you read secure usage, because it has important information about setting up networking, setting up party ID, and other stuff that are absolutely necessary. So even if you don't care about the C++ part, read secure usage. Okay. Then we have this demo part of the code. And in the demo, we have a bunch of examples that are written in Go and use some scenarios. And then we have this CMD. And the CMD is where we host this example demo that I just showed. Now, to be able to work with these demos, you need to have an understanding of where these wrappers are defined, right? Because we need a bridge from the demo code, which is pure Go implementation, to the C++ implementation. And that bridge is under demos cb-mpc Go. And the reason that we have put it under demo and not at the top level implementation is that this is still in work in progress. We don't have wrappers for everything yet. And once we do have it, then we'll move it to a top level, and then we will advertise it as production ready. So the C++ is fully audited, is production ready. The demo code, the Go wrapper, are a work in progress, although we are very happy with them. We don't see any problem with them yet. Okay, so now, under the demo, we have these internal stuff, which again, you don't need to worry about. All the dirty work of talking with C wrappers and all of that is happening here. So you can safely ignore all of that. What you do care about is this API part. And let's go, for example, to the MPC protocol, ECDSA MP. If I can find it, there it is. And you will see that if you want to, for example, create a new key, what functions to call, if you want to serialize or deserialize, what function to call. And if I can find the assign, sign request, there we go. So if you want to, for example, run an ECDSA threshold signature, this is what you would call. And in this workshop, you want to, instead of ECDSA signature, you want to use EDDSA. So to figure out what is the API and what is the inputs for that API, instead of going to this, instead of going here, you would go to EDDSA-MP and try to figure out how this works. And if you want to, for example, that's it. So I leave the rest of it vague for now, so that you can go and figure things out on your own. I don't want to give the solution away right away. And okay, so this is our wrappers. This is under demos go, cb-mpc go, API. That's where you go to figure out what you need to call. And if you want to know how this is called, so that you can figure out what you need to change, you can go to demos.go, cmd, and then threshold ECDSA, and you can either copy this directory or modify it in place. That's your choice. So the starting point is this main file, which is the web. I won't go into details of it. This is a simple implementation that's just using Go's HTML rendering to produce the HTML and sending it out. Again, I won't go into the details of it. What you do care about are actually in this handler. That's where you will change most of the code to achieve what we want to achieve. And the two interesting functions are the top of this handlers.go. One of them is called threshold DKG. The other one is called threshold sign. Okay. So anytime you want to run an MPC protocol, you would create a job object first. And a job object is a wrapper around the networking layer. Because you may choose to use MTLS as we suggest, or you may decide a different way of handling your networking. So as long as you pass something that implements this interface, we are fine. Then you create a job object, which you give the name of all the participants and the index and how many parties participate and whatnot, and then you're done. Do some sanity check. Application by application, it's different, and then you will call the API that I was alluding to. So this is the Go API that you can find under cb-mpc Go API. Okay, so you call this single API call does all the heavy lifting of the DKG, so you don't have to worry too much about what's happening under the hood, as long as you just know what function to call. That's it. And if you want to change it to support EDDSA, just go figure out what's the equivalent of this in the EDDSA. Similarly, for signing, you create the job object, and then you do whatever you need to do for signing. So in the case of ECDSA, different blockchains use different hash functions. Some use Kechak, some use double SHA-256 or whatever. And therefore, you need to choose what hashing functions you want to use. Then you need to
Excuse me, Arash, we stopped hearing you.
Okay. Is it good now? Is it back?
Yes.
Okay. So we said that we have this threshold concept or this access structure concept, right? So we have different participants, and then we choose from them who is going to participate. So those shares that belong to those different parties, we need to convert them to proper additive shares. Why? Because our MPC signing works on additive share. So you first do the conversion to additive shares, and then run the MPC protocol. So to convert to make this work with the EDDSA, you probably don't need this. You do need this. You need to call the proper EDDSA function here. Okay. And then when it's done, because in this demo I just wanted to show the signature outside in a OpenSSL format. Getting my share screen stops and then I get muted. I don't think I'm pressing on anything, but it happens. Am I back on?
Maybe it's the HADL01. Something.
All right. So yeah, I'm converting these to OpenSSL format and then outputting it. So if you want to change it to, for example, support the transaction or submit the transaction to Solana blockchain, then first of all you need to pass the proper message as input. Right? You need to create, instead of saying, hi, this is whatever, you need to create the transaction and then pass that as input. And then when you want to produce an output, you need to create the signature in a format that is understandable by Solana blockchain, not something that is understandable by, let's say, standard OpenSSL. So these are the changes that you need to make to support this. One final thing I will say, just so you know how regarding the access structure, because part of it is to change the access structure. And you see that the access structure is an input here. All right. So run threshold. All right. I have this function here, which is creating the access structure for. I'm saying that actually I'm going to pause here because defining what an access structure is and how it works is going to take maybe another 5 minutes of description. So any questions so far? Okay, so let me define what I mean by access structure and define a couple of words. So let's say you have 4 parties, P1, P2, P3, P4, right? And you want all of these, you want to force that all of these always participate. In our terminology, you need to create a tree, put an AND node at the top, and then make all of these the children of them. Okay? This is an access structure that essentially has a single AND node. What if you want to have an access structure that is threshold based, meaning that you want maybe 2 out of 4 to participate? Then you would create a threshold with a parameter 2 and then make all of these its children. So now this is a threshold access structure. And we also have an OR, meaning that either of them. So we can have, for example, an OR node and say P1, P2. So either P1 or P2 can participate. Given these 3, you can create any complicated access structure you want. So for example, you can say, I want to make sure that the CFO participates. So P1 is going to be our CFO. And then I want to say that either the CEO or because it is either, it will be an OR node. So either CEO or CEO can participate, right? So by combining these nodes into a tree, you can create all sorts of different access structure, okay? And how this is presented in the code, let me show you how this works in the code. Okay, so for example, in this demo, we have a root, which is a threshold node, and the input 2, 3, whatever is we are receiving from the web UI, and then we are creating a bunch of children for that. And these children are just normal leaves. They are not anything more complicated. And so if you want to, in this workshop, if you want to use a different access structure, you would go and change this function, and then that's it. Everything else should work. If you decide to add more parties, because right now the code works with 4 parties. If you want to make it 5 parties and more, I suggest you do it later on because that's going to take a little bit of time since you need to create a configuration for them, make sure they have their own certificates and all of that. So play within the 4 parties for this for the purpose of this workshop. Any questions? Everyone following? Any things? Regarding access structure question. Oh, that's Yehuda is answering. Okay, never mind. All right. If everyone is following and it's understandable, then I can talk about the disaster recovery and verifiable encryption. So that also needs a little bit of description first before going over the code. So let's say we have this our example, which we have 4 parties, P1, P2, P3. Actually, let's just choose a different thing. Let's see, these are our parties, and we have a threshold of 2. So 2 of these need to participate. Each of them are going to have their own secret share, right? They are going to have K1, K2, K3, okay? And we want to back them up. These are scalars, and they have a corresponding points on the elliptic curve, right? So we have Q3, similarly we have Q2, we have Q1. If you go and just simply encrypt K1 with AES and upload it to any cloud provider or any storage that you want to use for your backup, then or for example, give it to someone else to safeguard it for you, whoever that third party may be. You may not know whether something was corrupted in transition, right? So on the receiver end, if they want to check whether they got the correct backup, the correct encryption or not, they cannot do that unless they go decrypt it and then decrypt it and then come do this multiplication themselves and get Q1, and that's how they would know that they got the wrong thing, right? But that's an awful way of doing things, because then that third party now knows your secret share. What we want to do is that we want to still encrypt K1, give it to a third party to back up for us, but we want that third party, or anyone else for that matter, to be able to verify and make sure that the encryption is correct. That's a property that we call public verifiable encryption. Okay? And this public verifiable encryption is something that we have implemented and added to the library, and we have made it work with access structure as well, meaning that you don't just encrypt it and give it to a single person. you can encrypt and back up your key share and require so that maybe 4 other people need to get together so that they can decrypt and obtain your key share. So to back up this K1, you can use a completely different access structure. To back up this K3, you can use some other access structure. To back up K2, you can use some other access structure. So to back up any of these, you can optionally use a different access structure, completely different from the original access structure. Okay, so that's why if you look at the, let me share the code. If you look at the code sample, where is it? Our PVE gets an access structure as input, and it does not necessarily have to be the same access structure as done during the signing. So to get an idea how this PVE works, you can see an example under Demos Go, example ECDSA MPC with backup. So here, starting from step 2, you will see how we are creating an access structure. We are simulating, for example, having key shares. Then we are encrypting those key shares, and we can publicly verify those key shares. And then finally, if needed, decrypting. I just put a disclaimer here in case you go through this and then things may look weird to you, that for the decryption, we are requiring all the private keys, meaning that for when we want to decrypt, those decryptors, the access structure for the decryptors, a quorum of them need to get together to decrypt in one place. Okay? This is because this is slightly different from, well, not slightly, very different from how we do it in Coinbase. And we chose to expose this simplified way of doing things in open source because in the initial release, our thought was that this sort of disaster recovery situation is a break glass, situation shouldn't happen very often, and if that happens, then that's fine. Let's get everyone together to help with the decryption. So that's how it is in this version, but in the future releases we will make it so that even for the decryption you don't need everyone to be in the same place, and the decryption can be distributed as well. So I just wanted to give you a heads up that at this point, the decryption, you need everyone in one place. All right. That's it, essentially. I don't know how much more time we have and where is everyone in terms of progression through the demo.
Can you hear me, Arash?
Yes, I can.
Yeah. Thank you so much for the walkthrough. I'm wondering if we can do some change the configuration a little bit of the Go file and see in the front end and how we can tweak our MPC setup.
Sure. So what kind of configuration do you have in mind? I mean, what's the goal? Do you want to see where do I change so that the UI change, or what's the goal of this?
I mean, maybe submit a complex transaction on Solana or something like this, or like see like how it works when we connect all the dots?
Oh, okay. So yeah, changing it live is going to be, because there are a lot of changes, but I can show you the final result.
Yeah.
So if you have that in mind, you can see what it will end up look like. So yeah, skipping the access structure stuff, the Solana part is the more okay. So let's go to the web. Run threshold sign, and then we need a message. Okay, there it is. So this is again, this is just for the purpose of demo. That's why I'm just hard coding a bunch of the stuff, the receiver address and the from address. But you can easily get them, and I will show you how you can easily get them from the DKG. So to create a Solana transaction, you just call this API, and then you pass in the amount that you want to send, and who is the recipient, what's the recent block hash, and who is paying for this. So once you have the transaction, you get the transaction, the raw transaction message out of it and marshal it into binary. Okay. And now I'm encoding it to a string just because in this demo, the leader is sending the message to everybody else, and I wanted to send it in a base 64. This is not necessary. This encoding is not necessary. It's only needed for the purpose of this demo. All right. So we have the message content. Now that the message content, everyone should sign on it. In this case, the actual signing of the message doesn't change much, right? Because we, as I said in the initial description, we just remove the hashing of the message because the message is already correct, and EDDSA signing doesn't require the hashing. This is again because of that decoding. In a real application, you wouldn't need to do that. And then you simply, instead of ECDSA sign, you call EDDSA sign. That's all there is to it. Okay. Then now you need to produce a signature. You need to send the signature out, and actually it's quite simple. You just use that. So in the ECDSA, you need some conversion to make it work with the outside world, but EDDSA, our signature is already compatible with the standard and with the standard. So
It happened again. You're muted and your screen is not sharing.
So weird. I don't know why that happens. Okay, so I don't know when it happened, but let me repeat the last thing. So in the ECDSA signature, you need to convert the byte array that we return into the proper ECDSA standard format. But for EDDSA, the byte array that we are returning is already good, so you don't need to do anything essentially. So you get the signature. Once you get the signature, you need to submit it to blockchain. Okay, so we have this signature, and we had that transaction. So we just said we just say that we just assign the signature to the transaction object, and this is just for pretty printing. And then you connect to the client and submit the transaction. That's it. So the majority of the change is essentially figuring out how to construct the Solana transaction and how to submit that transaction to blockchain. The actual MPC work is very straightforward. Just change CDSA to EDSA and then we're done.
Very cool. I would expect to see some demo with base chain since it's Coinbase, but
Yeah. We didn't want it to make it too Coinbase heavy, but yes, the standard CDSA would have worked for base chain as well.
cool. Any more questions? You guys, feel free to ask your questions. If you're able to run the demos on your end, also let us know. Vertex is saying that he has a build there, and on which stage? We need some more context, yeah. Hey guys, if you want to ask Yuda or Arash some personal questions, feel free.
Bertus, yeah, I need to see the error if you can paste the error. Yeah. Sleep Crypto is our MPC library. Are you sure you did sudo make install? Because that's the thing that installs the C++ library. Without that, Go wouldn't be able to find it and therefore will complain about that.
Okay, I would like to ask some personal questions in the meantime. To Yuda and Arash, how long have you been working in Coinbase? And as the cryptography team, are you working on mainly the exchange, MPC infrastructure and code, or also on the chain itself, like the sequencer and everything that relates to the L2 Obstack chain?
I can go first. Yeah, if you want. Yeah. I've been working in Coinbase a little bit over 4 years, I think. But yeah, around 4 years. And we are at the and also this answers some of the last question. We are at the core underlying part of the stack, meaning that we provide the generic solution for the rest of the company. So whether it is Algorand or Solana or Base or whatever, as long as the signing algorithm is the same, then our work doesn't change too much. For some blockchains, we need to do a little bit more work, but mostly we are blockchain agnostic. And Yuda, correct me if I'm wrong.
Yeah, so yeah, our team does see other cryptography across the organization, but primarily we're working on the protecting the keys, on the key management. That's what we do. I've been in Coinbase for 3.5 years. Arash is 4 years. He just says they're not hearing us.
Oh,
can nobody hear me?
Yeah, I can hear you perfectly. That's weird.
Okay.
Okay. I heard everything, to be honest. Yeah.
I also heard. Anyway, so yeah, we've been Arash is just over 4 years, I think. But our main responsibility is protecting all of the assets under management at Coinbase. But we're also looking at other parts of cryptography as well where it's used.
Cool. We have two questions from Sartak and Amit.
The second question is hard. I let you you take that. I can answer the technical one. So the how do we bridge C++ Go implementation with our TypeScript? So if you are building, for example, a TypeScript or Node.js kind of base server, then you need to call the C wrapper. So if you remember, I said that we have a C++ core library. On top of that, there is this very lightweight C wrapper. And then on top of that is the actual Go library. So if you want to use it in any other language, the C wrapper is going to be the same. So you can copy paste those, but then you need to write your own TypeScript or Python or whatever else you may need to call those C wrappers and then expose whatever API you want to the rest of the TypeScript.
So Amit's question, how did I get into the field? I guess it's a lot by chance. I did my undergrad without thinking I would go to masters, but it just I was interested, so I did a master's in data mining. I guess today we would call it AI. And then I wanted something more rigorous, something which was had stronger theoretical foundations. So I went to the Weizmann Institute for my PhD, and I started working with some. I took courses in complexity, cryptography. I was very attracted to the field because it was, on the one hand, very theoretical and therefore very clean and elegant, but also very close to practice. So you could be both at the same time. And I guess that's something I really like about being in cryptography in general. What I'm most excited about in the field in the future, there's a lot going on in many areas. I don't know. It's a lot. The whole field, like MPC developments, ZK, a lot is happening. Yeah. What do I hate most about my work? Well, that is a personal one, almost. You ask personal questions. I thought, how many kids do you have? What do you hate about your life? This is about your work. It's not that personal. So what do I hate most about my work? I don't think I hate anything about my work right now. I'm very happy. So what do I like most about it? I think I like the fact that we're doing real product-driven research. So we need to do real research, but not playing around with abstract ideas and then hoping the organization will adopt it. It's the other way around. We have real product requirements that require developing new cryptography. And so that's a really exciting process. Getting those requirements, doing the research, writing it up, proving it, getting it verified internally, externally. I think it's an amazing job. Any tips to share with the community? Give me a clue in what direction. Tips could be anything.
Anything you would like to share that you think would be of value? I think you have a lot of value to add, not only in the MPC world.
It's just so broad. I don't know what to say.
You don't have to, but if you have anything to share, we would love to hear it.
I don't know. I could just say what I tell my kids. I believe that working hard in the end pays off. So work hard, eventually be worth your while. Do the right thing and it works out.
Johnny, would you like to give us some tips as well for the community?
Yeah, like Yuda said, it's really broad. In what sense? I want to say some things about MPC. I think I'm mostly focused on like smart contract security risks. And I think the key management and client-side attacks are very common, and we see many hacks that are due to improper key management, key leakage, or phishing attacks on clients. And I think this is an untapped. It's like an area that we need to focus more in terms of security. And I think this open source library that was released will significantly enhance the security of the industry, and it's great because if you just go to DeFi Llama and go to the hack section, you'll see that like every 4 attacks, one of them is like private key compromise, and so on and so forth. So thank you for releasing it and for the great workshop.
Thank you very much. I just want to have a call out to Arash, who was a driving force behind the library itself in Coinbase. As I said in the beginning, me and code. I did write code in the 1990s, but since that was the last time I wrote code, nobody lets me near a keyboard. Maybe put a semicolon at the end of the line to let me do that, because that's a C++ part. You don't even need that in Go anymore. So this is real kudos to Arash for leading this effort.
Thank you. All right. Yeah. Thanks, Theoda, for the kind words, and thanks everyone, Amit and Johnny, for hosting this. Please check us out at the our GitHub repository, and you can find how to contact us there. You can send us an email. I think it's cb-mpc@coinbase.com. You can find it on the repo. Open an issue if you have a problem. And as Yehuda mentioned, if you find any bugs, vulnerabilities, please submit a HackerOne, and you may get some bounty, and we'll help
Or
us.
you can reach out directly. If you prefer not to go the bug bounty route, you can also just reach out.
Absolutely.
Awesome. Thank you so much, guys. It was a pleasure. And thank you, Yuda and Arash. It was amazing. And Johnny for the moderation.
Thank you.
And thank you everyone who attended. If you would like to see it later or rewind anything, you can watch it on YouTube, Telegram, or LinkedIn. And see you next time.
Bye.
Bye for now.